Good morning and welcome back to Chapter 9. Today we're looking at Section 2, which is about Taylor series. A Taylor series is a power series. It's just a specific power series. We can do a lot with it, though. In fact, a lot of the power series we looked at last time were actually Taylor series. So, our learning targets, we're going to construct Taylor polynomials of different orders. So a Taylor polynomial is just part of the Taylor series. A Taylor series would be an infinite series. A Taylor polynomial is like the partial sum. And then construct terms of Mclaren Taylor series generated by functions. A Mclaren series is a special case of Taylor series, actually, where it's just a Taylor series centered at 0. So we'll be talking about those. First, we have a little exploration idea here. So we're going to construct a polynomial that's going to be p of x equals a naught, so a constant plus something x squared plus something x cubed plus something x to the fourth with the following behavior at x equals 0. So we need, at 0, we want it to equal 5, which means if we plug in 0 to everything, we need to get 5. So we have p of 0, which will be 5, which will be a naught plus a1 times 0 plus a2 times 0 squared plus a3 times 0 cubed plus a4 times 0 to the fourth. So as we might imagine, all these zeros are going to multiply to be 0. So a naught equals 5. Because p of 0 equals 5. All right. Now we need the derivative at 0 to equal 7. So first we need to find the derivative. P prime of x, well, the a naught's a constant that goes away. So we'll have a1 plus 2 a squared x plus 3 a cubed x squared plus 4 a to the 4 x cubed. So now when we plug in for 0, it's going to have to equal 7. And so we'll have a1 plus, and then everything else has an x in it, so we're going to have a whole bunch of zeros, just like we had for that first one. So a1 equals 7. All right, how about the next one? We need the second derivative to equal 11. So first we need to find the second derivative. The a1 is going to go away because that's a constant. So we'll have 2a2 plus, so we'll multiply to get 6a3x plus 12a4x squared. All right, plug in 0. And it's going to have to equal 11, which will equal 2a squared plus, and then the other two things are going to have zeros because the x's are zeros. So we can then divide to get a2 equals 11 over 2. So we're finding all of our constants for our polynomial here. The third derivative is going to have to equal 13. So first let's find that third derivative. So from the second derivative, the 2a2 goes away. So we'll have 6a3 plus, then we multiply by 2 to get 24a4x. Plug in 0 for that. We're going to have to get 13 will equal 6a3, and then the 24a4 times 0 is going to be 0. We can divide by 6 to get a3 is going to be 13 over 6. And then finally, the fourth derivative, which if we find the derivative, the 6a3 goes away. So we have 24a4. And that's just a constant, so when we plug in 0, we're going to get 24. That wasn't 24 at all. That was a 44. It's 17 will equal 24a4. So a4 will be 17 over 24. So we found all these coefficients. So we can make the polynomial. We just plug in those coefficients. So p of x will equal a0, which was 5, plus a1x. a1 was 7, so 7x, plus a2, x squared. a2 is 11 over 2, x squared, plus a3x cubed. So that was 13 over 6x cubed, plus a4 x to the fourth, which was 17 over 24x to the fourth. And so that would be that polynomial. Something, and you could do that with any polynomial like that, by the way. Something to notice here is that the denominators, we have over 1, so we have 1, 1, 2, 6, 24. If we think about how we got these, 6 was 2 times 3. 24 was 2 times 3 times 4. 2 was 2 times 1. 1, 1. These are factorials. 0 to the 1, 1 to the 1, or 0 factorial, 1 factorial, 2 factorial, 3 factorial, and 4 factorial. So those factorials in the denominator are going to be important. Notice what the numerators are. 5, 7, 11, 13, 17. Where do we see those numbers? Those are the derivatives at those points. And so what we have here is each of these terms is going to be a derivative over the factorial for n. So we'd have x to the n, we have an n factorial in the denominator, and then we have the nth derivative. I'll use p to the n of 0. And that's going to be what each of these terms are. This is an important thing that we're going to be seeing today, because that's what makes these Taylor series, Taylor polynomials, Mclaren polynomials. So let's look at a very similar one. So construct a polynomial. It's the same thing that matches the behavior of natural log of 1 plus x at x equals 0 through the first 4 derivatives. So we're going to have to find those first 4 derivatives and plug in 0, because as we saw that last time, each of those a values is going to be the derivative divided by the n factorial. So if we start out, p of 0 equals natural log of 1 plus x, so we plug in 0, we get natural log of 1, which equals 0. So that's a0, a0. The next one, we're going to take the derivative and then plug in 0. So the derivative of natural log of 1 plus x, p prime of x, is going to be 1 over 1 plus x. Then chain rule, the derivative of 1 plus x is 1. So that's fine. Plug in 0. We get 1 over p prime of 0 is 1 over 1, which is 1. The second derivative, well, the first derivative, that 1 over 1 plus x, could be written as 1 plus x to the negative 1, which will help out here, because the second derivative will be negative 1 times 1 plus x to the negative 2. Plug in 0. We get 1 plus 0 is 1, to the negative 2 is 1, throw that negative on it, so we get negative 1. the third derivative, multiply by that -2 to get +2, 1 plus x to the -3, plug in 0, 1 plus 0 is 1 to -3 is 1 times 2 is 2. Take the fourth derivative of x, multiply by that -3 to get -6 times 1 plus x to the -4. Plug 0 into that. 1 plus 0 is 1 to -4 is 1 times -6. So now we have each of these, we have each of our derivative values. If we found the derivatives like we did last time, we'd find that, oh, hey, we're going to have to divide each of them by n factorial, which we could do. We could find the derivatives of this polynomial, but we don't need to, because what we'll see is p of x will equal a naught is just 0 plus, and then a1 we have to divide by that 1 factorial, so which is 1, so we have just 1 times x, plus a2, which was, for the second derivative, is -1 over 2 factorial x squared, plus a3, which is from the third derivative, which is 2 over 3 factorial x cubed, plus a4, which was -6 over 4 factorial x to the fourth. We can simplify this a little bit. P of x equals 0. We don't need to have a 0 there. So we have x minus 2 factorial is 2, so that's minus 1/2 x squared. 3 factorial is 3 times 2. That 2 cancels, so we have a plus 1/3 x cubed. Then we have a minus 4 is 2 times 3 times, or 4 factorial is 2 times 3 times 4. 6 was 2 times 3, so those will cancel to give us 1 over 4 x to the fourth. And so this polynomial is a fourth degree polynomial that's going to match the behavior of the natural log of 1 over x around x equals 0. Natural log of 1 plus x around x equals 0. I don't think I put a graph on this one here. I guess we're about to find out. Now, it won't match it forever, but for that little area, it will. Where can this be helpful? We can plug values into this polynomial. If we wanted to find it for like 0.1, we could plug in those 0.1 values and get a number. Like we can do 0.1 squared, 0.1 cubed, 0.1 to the fourth. It might not be as pleasant as we would hope, depending on the numbers that we're using, but we can do it. Well, what would the natural log of 1.1 be? You're not going to be able to calculate that. Yes, you can use a calculator, but how did the calculators do it? How did they figure out how to do this in the beginning? So this was super, super important back in the day. It still is important because there are certain functions that we cannot deal with as a function, but as a Taylor series, they actually work out fairly well. Let's do another one. We construct the seventh order Taylor polynomial for the Taylor series for sine x at x equals 0. So we're going to go till we get to x to the seventh. So we'll need the seventh derivative. But this is sine x, and so it's going to start alternating here pretty soon. So f of x equals sine x, which means f of 0 equals 0. F prime of x equals cosine x. So f prime of 0 equals 1. Double prime of x equals negative sine x. F double prime of 0 equals 0, because sine x is 0. F triple prime of x is negative cosine x. So the third derivative of 0 will be negative 1. The fourth derivative, negative cosine, will take us back to sine of x, which means the fourth derivative is 0. And then it's going to repeat. So the fifth derivative will be cosine, which will be 1. The sixth derivative, which will be negative sine, will be 0. And the seventh derivative at 0, which is negative cosine, will be negative 1. All right, so now we can make this polynomial. P of x will have the first one, which is 0, and then it would be over 0 factorial, which is 1, so that's why we don't usually put that, plus 1 over 1 factorial x, plus 0 over 2 factorial x squared, plus negative 1 over 3 factorial x cubed, plus 0 over 4 factorial x to the fourth, plus 1 over 5 factorial x to the fifth, plus 0 over 6 factorial x to the sixth, plus negative 1 over 7 factorial x to the seventh. All right, well, this will simplify significantly because we've got a lot of zeros in there. So P of x equals 0, that's 0. So 1 over 1 factorial is just x, 0x squared minus 1 over 3 factorial x cubed. 3 factorial is just 3 times 2 times 1, which is 6, or we could leave it as 3 factorial. Leaving it as 3 factorial will actually help us with the equation. X cubed plus, we have 0x to the fourths, 1 over 5 factorial x to the fifth, no x to the sixth, and then minus 1 over 7 factorial x to the seventh. And so this is a polynomial that will approximate sine actually pretty closely around when x is 0. I do have a graph of this one. It'll be on the next slide. But before we get there, that's the Taylor polynomial. That's the 7th order Taylor polynomial. Because we get up to x to the 7th, it's a 7th degree. That doesn't have to happen that way. For instance, if we wanted the 8th order Taylor polynomial, we'd go out to x to the 8th. Well, that's going to be one of those 0 terms. So the 8th order Taylor polynomial is actually exactly the same as this one, because we'd have plus 0 over 8 factorial x to the 8th, and that term would cancel. So it doesn't have to be the same degree. It should be pretty close, though. And the only reason why it wouldn't be the same degree is because it had a 0 term at that degree. So that's the Taylor polynomial. If we want to get the Taylor series, we're going to need to take this out indefinitely. And so we'd have to add, and so we'll get the sum. We have some sigma notation here. We're going to start out with n equals 0. We're going to go to infinity. And then we just need to make an equation for this. So the first thing, it's alternating from negative to positive, which means we're going to have to be multiplying by a -1, either to an n or an n plus 1. Well, when we plug in 0, -1 to the 0 is positive. The 0th term is positive. -1 to the first is negative. That first term is negative because this one's the 0th term. This one's the first term. So the n works. If these signs were flipped, if it was -x plus the x cubed minus the x to the 5th, then we'd have n plus 1 because we'd have to offset it by 1. All right, and then we have the factorials. So we have 1 over, we're going to have factorials. So when n equals 0, it's a first factorial, and here we can just look at the first term, second term, third term. We don't need to worry about all the zeros that were in there because we'd have to deal with those. So we have 1, 3, 5, 7. So those are odds. How do we get odd numbers? We go 2n, and so 2 times 0 is 0 plus 1. And so then for the first term, 2 times 1 is going to be 2 plus 1. That's 3 factorial. And then the exponent is going to be the same thing, x to the 2n plus 1, because that will get us those odd exponents. So just taking what we have and turning it into this series, because we'll be able to do stuff with these series here in the fairly near future. But we have infinite sums for series, among other things. So let's take a look at this graph. So this is for each term. So the y1 term just equals x. That's just the line. So looking around in here, it actually matches the sine graph fairly well. But as we continue, the second term, when we subtract that x cubed over 3 factorial, now all of a sudden we have this cubic, which matches basically perfectly from there to there. The next term, when we add the x to the 5th 5 over 5 factorial, it's matching. When we take that x to the 7th, it's actually matching all the way. So let's see, the x is going from -2 pi to 2 pi, so that would be about from -pi to pi. It's matching, so that gives us a really good one. As we keep going, it gets closer and closer. If we look at this 17th one, it's matching from -2 pi to +2 pi. Now it will vary because polynomials, they're boundless. It will increase and decrease without bound, whereas the sine graph stays in between -1, +1. However, as we take this out to infinity, we will match the sine graph perfectly. That does not always happen. It does not always happen. We cannot always converge. That's what that calls. Like as we go to infinity, the polynomial will converge on the function. Sometimes it'll only happen within a certain section. But in this case, as we go to infinity, it will actually converge on the function. So the sine graph could be written as that infinite series. So a little bit more formal here. The f is a function with the derivatives on all orders through some open interval containing 0. Then the Taylor series for f centered at x equals 0, which is called a Mclaren series. Taylor series don't always have to be centered at 0, but when they are, it's a Mclaren series. That's important to know because if they say find a Mclaren series, you need to know that that's centered at 0. it equals what we've seen. So it's the kth derivative of 0 from k equals 0 to infinity, or the sum from k equals 0 to infinity. We have the kth derivative over k factorial times x to the k. So it's what we've seen a couple times already. And the partial sum, we just go up to a certain point. We stop at a certain point. And that's the Taylor polynomial. So we did the partial sum with x of the fourth sum, because we went up to x to the fourth. We did the seventh one with sine. We went to x to the seventh. So let's find the fourth order polynomial that approximates y equals cosine of 2x near x equals 0. So we have y is cosine of 2x, which means y of 0 is going to be cosine of 0, which is 1. We're going to need to find the first four derivatives, so y prime. Cosine of 2x would be negative sine, but then we have to multiply by that 2, so that's going to be negative 2 sine of 2x. Y double prime. Sine will give us cosine, but again we have to chain rule that 2, so we're going to have negative 4 cosine of 2x. The third derivative, cosine will give us negative sine, so that'll be positive now. I have to chain rule to get 8 sine of 2x. And then the fourth derivative, sine will give us cosine. Chain rule again to get 16 cosine of 2x. Now when we start plugging in zeros, sine of 0 equals 0, so that's 0. Cosine will equal 1, so that's 1 times negative 4 is negative 4. Sine is going to be again 0, and cosine's 1, so this will be 16. Alright, so now our polynomial, the fourth order polynomial, is going to be the first one, so just 1, plus, then we have 0 over 1 factorial x, plus negative 4 over 2 factorial x squared, plus 0 over 3 factorial x cubed, plus 16 over 4 factorial x to the fourth. So again, that's just straight into the equation. The equation is kind of big and complicated. However, it's the same thing over and over and over. So just a little bit of practice and it gets actually pretty easy. Let's simplify this. So I have 1 plus 0. All right, so let's see, 2 factorial is 2. So that's be minus 2x squared. Then we have 0x cubed. 4 factorial is 4 times 3 times 2, so 8 times 3. We can simplify to get us 2/3 x to the fourth. So this is going to be a fourth order Taylor polynomial that will approximate cosine of 2x. How close is it? Well, if we graphed it, we have cosine is the red, and the blue is this polynomial. And it looks like from about -1 to +1, actually, it hits it pretty much perfectly. The more we do, the better we'll get. Like the more places out we go, the better the estimate we'll get, the better the polynomial we'll get. But if we're trying to figure out like what is cosine of 1/2, we could plug 1/2 into, well, cosine of 2 times 1/2, which would be cosine of 1. We could plug 1/2 into this equation and get a really, really good estimate. We don't have to center them at A or at 0. Again, a Mclaren series is centered at 0, but we can center it anywhere we want. The nice thing is, so we're going to plug in whatever value we're looking for into our derivatives. Other than that, it's just a horizontal shift. Instead of x squared, x cubed, we just have x minus a. It's just a horizontal shift. So if we want to look at f of x equals e to the x, centered at x equals 2, we're going to find the Taylor series. So we're going to need that infinite series. And so we're going to need to find a few terms so we can figure out exactly what this one is. Although we'll see we could actually just plug it right into this equation as well, because the nth derivative at a, but just because it's e to the x. Let's find a few. So we'll have f of x equals e to the x, which means f of 2 equals e squared. F prime of x equals e to the x, so f prime of 2 equals e squared. In fact, all of our derivatives are going to be that way. All the derivatives are just going to be e squared. So our p of x will have the first one, which is e squared, over 1 factorial, or 0 factorial, plus e squared over 1 factorial times x minus 2, plus e squared over 2 factorial times x minus 2 squared, plus e squared over 3 factorial times x minus 2 to the third. And we can keep going with that. So our series here, we're going to go from, we could use k, we could use n. This is using k, I'm going to use n. N equals 0 to infinity. We're not changing signs or anything like that. So we'll have the derivative, or the numerator here is just e squared over, we'll have n factorial times x minus 2 to the n. And that's what we see here. We have 0 factorial, 1 factorial, so 0, 1, 2, 3, all factorials, the e squared, and then x minus 2 to the n. And that's that series. If we want to look at the graph, the red one is the e to the x, and the blue one is the series. I took it out to a few. I took it out to, I cannot remember how many I took it out, but not a ton. That's just, it's the third degree. So it's actually what I have written here. And notice, like, it starts to diverge up there, but it converges for a long ways there. So find the third order Taylor polynomial for this polynomial. So we found Taylor polynomials for other polynomials, well, or for other things that are not polynomials. Well, what about for a polynomial? The nice thing, centered at x equals 0, it's just f of x. Like, this is, it's 2x cubed minus 3x squared plus 4x minus 5. That is the Taylor polynomial centered at 0. So centered at 0, it doesn't actually change at all. Centered at something else, we just need to find the pieces. So f of 1 will have 2 minus 3 plus 4 minus 5, which is negative 2. F prime of x is going to be 6x squared minus 6x plus 4. So f prime of 1 was 6 minus 6 plus 4, which is 4. F double prime of x is going to be 12x minus 6. So f double prime of 1 is 12 minus 6, which is 6. And then we're doing a third order, so the third one of x is 12, and so of 1 it's 12. So we can plug this in. So f of x will equal the first one, so negative 2, plus the second one was 4 over 1 factorial times x minus 1, plus 6 over 2 factorial times x minus 1 squared, plus 12 over 3 factorial times x minus 1 cubed. We can simplify that just a little bit. Negative 2 plus 4 x minus 1 plus 2 factorial is 2, so this will be 3 x minus 1 squared plus 3 factorial is 6, so that's going to be 2 x minus 1 cubed. And so this is actually the same exact polynomial, because a polynomial can be written as a polynomial. This, as opposed to powers of x, this is just powers of x minus 1. So it's almost like we had it shifted, but then recorrected. You could actually find that out if you multiplied these out, like you squared and you cubed those things and simplified, you would get back to that original polynomial. So that's how we can write polynomials centered at different things. You do this exact same thing. If we had like 4th degree, 5th degree, whatever, like all the derivatives after the third one here would be 0. And so we'd have plus 0, plus 0, plus 0, plus 0, because we don't have 4th, 5th, 6th degree terms here. And so the polynomials, like when you rewrite those as a Taylor polynomial, it is exact. It is the same thing, just with powers of something different. Again, here we have powers of x minus 1 instead of powers of x. Building series. So if we wanted to find the Mclaren series for something like this, f of x equals e to the 2x minus 1 over 3, and then give its interval of convergence, that's where it converges. We, like, starting from here, if we're thinking it's like, oh, okay, we need to do the derivatives of this, that would be tough. So let's look at a simpler problem first. Let's look at just e to the x. So I won't use f of x, we'll use y equals e to the x. Now we did centered at 2 earlier, and this is going to be close. So y of 0 equals e to the 0, which is 1. Y prime equals e to the x, so y prime of 0 equals 1. Y double prime equals e to the x, which means that y double prime of 0 equals 1, etc., etc. So we can make e to the x. E to the x is going to be 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus, and we can keep going with that. We could write it as a series if we want as well, because that's going to equal the sum from n equals 0 to infinity of, we have 1 over n factorial times x to the n. So just x to the n over n factorial. So that's e to the x. All right, well, what if we want e to the 2x? We're just going to replace all the x's with 2x's. 1 plus 2x plus 1 over 2 factorial times 2x squared plus 1 over 3 factorial times 2x cubed. We can even include it here. So we have 2x to the n over n factorial, which could also be n equals 0 to infinity. We could go 2 to the n, x to the n over n factorial as well. So that's a 2x. All right, minus 1. Well, if we have e to the 2x minus 1, that's going to just take what we had and then subtract 1. That subtracting 1 is going to get rid of that value because we have 1 plus a whole bunch of stuff minus 1. That goes away. So we end up with 2x plus 1 over 2 factorial times 2x squared plus 1 over 3 factorial times 2x cubed plus ... And so what does that do to our series here? It subtracts 1. It shifts everything. Like in this case, it shifted everything over 1. And so we would go, let's see, we could just start at n equals 1 to infinity, 2n xn over n factorial. Or the other thing we could have done is we could have still started at 0, but then each of the n's would be, we'd have to subtract 1, add 1. If it was 0, we had to turn it to 1, we'd have to add 1. So it could also have been n equals 0 to infinity of 2 n plus 1 x n plus 1 over n plus 1 factorial. So we would have just added 1 because each of our terms, like our first term became the 0th term. And so we'd have to uncorrect for that. So either of those two would work there. And then if we wanted to divide by 3, e to the 2x minus 1 over 3, we would just divide everything by 3. We'd have 2/3 x plus 1 over 3 times 2 factorial times 2x squared plus 1 over 3 times 3 factorial times 2x cubed plus ... plus, or no, equals. And then here I'm going to stick with n equals 1 to infinity. We would just multiply the denominator by 3. And so taking this one, we could start out with our easier problem, and then we can do those operations on the sequence, and then see what happens with the series and the summation notation afterwards. So having some basic series are kind of nice. We found a few. We found e to the x right here. We found natural log of 1 plus x. We found sine of x, but there's a few more that are good to have on hand. Oh, and it's interval of convergence. We'll be talking a lot about convergence in the next few sections, but e to the x converges for everything. So it means that this equals e to the x. Like as it goes to infinity, it converges for all values of x. And so this new one also converges because we didn't do anything that would have changed that. So some common Mclaren series. We have 1 over 1 minus x, just gives us 1 plus x squared plus x cubed plus, as long as x is less than 1. These are the intervals of convergence over here. So when x is in between -1 and 1, it converges. Bigger than that, it does not. 1 over 1 plus x, it's 1 minus x plus x squared. So it's just the alternating series. E to the x, we saw that one. That converges for everything. Sine of x, we saw that one. That converges for everything. Cosine is going to be similar to sine, except that it has the other terms because the zeros and the ones are switched. Natural log of 1 over x, we saw that one, actually. That converges for x has to be greater than -1 but less than or equal to 1. It can't equal -1 because then you have natural log of 0, and that's undefined. And then inverse tangent converges when the absolute value of x is less than or equal to 1. And that gets us that x minus x cubed over 3 plus x to the 5th over 5, which we saw actually in that first one. No, those weren't alternating. So these are just some common ones that you'll want to be using to build some different ones like we just did. Cool thing to notice, though, if we look at this natural log of 1 over x, what's the derivative of natural log of 1 over x, or of 1 plus x? It's 1 over 1 plus x. That is the derivative. If we look at the terms, the derivative of x is 1. The derivative, so minus x squared over 2, that derivative would be x, plus x cubed over 3, that would be plus x squared. And so we could take the derivative term by term and get the derivative. We can do the same thing with the integral. That's coming up in another section or two. Right now, we're just using it to build other Taylor series. So, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.